My name is Shannon Kemp, and I'm the Chief Digital Officer for Dataversity. We would like to thank you for joining today's Dataversity webinar, Data Modeling Types, Conceptual, Physical, and Logical. It is the latest installment in a monthly series called Data Ed Online with Dr. Peter Aiken. Just a couple of points to get us started. Due to the large number of people that attend these sessions, you will be muted during the webinar. For questions, we'll be collecting them via the Q&A section. And if you'd like to chat with us or with each other, we certainly encourage you to do so. And just to note, Zoom chat defaults send to just the panelists, but you may absolutely change that to network with everyone. To open the Q&A or the chat panel, you can find those icons in the bottom middle of your screen for those features. And to answer the most commonly asked questions, as always, we will send a follow-up email to all registrants within 2 business days containing links to the slides. And yes, we are recording and will likewise send a link to the recording of this session as well as any additional information requested throughout the webinar. Now, let me introduce to you our speaker for today, Dr. Peter Aiken. Peter is an acknowledged data management authority and associate professor at Virginia Commonwealth University, president of DAMA International, and associate director of the MIT International Society of Chief Data Officers. For more than 35 years, Peter has learned from working with hundreds of data management practices in 30 countries, including some of the world's most important. Among his 12 books are many firsts, starting before Google, before data was big, and before data science. Peter has founded several organizations that have helped more than 200 organizations leverage data-specific savings, which have been measured at more than 1.5 billion US dollars. His latest is Anything Awesome. And with that, let me turn everything over to Peter to get today's webinar started. Hello and welcome.
Hi, Shannon. I'm sure you didn't mean to turn everything over to me. That would be an insane proposition, but it's good to talk to you. And it's 96 degrees here on the East Coast of the US. So hopefully everybody's staying cool and ready for some very much eating from a fire hose, drinking from a fire hose, talk about the differences between these 3 modeling types. So just jumping right into the program, I'll start off with a little bit of introductory material about data modeling in general on this. Then we'll talk about the 3 types, conceptual, logical, and physical, and the differences between them, and then finish up with a good deal of takeaways around this, as well as a fair amount of reference material. And this is the wonderful thing about our community that Dataversity has built here for us. I've had several people contribute additional materials here that we'll be including with the slides as well on this, and I'll call them out as we get closer to the end. So as Shannon said, let's just jump right in and talk about data modeling. And before we talk about data modeling, we might talk about how much data. And this was a wonderful little infographic from a company called domo.com. And for some reason, they stopped doing this, which is really unfortunate. But the last year they did it, they showed that for every minute of the entirety of 2022, when we were coming out of the pandemic, Facebook users shared 1.7 million pieces of content. That's every minute of the entirety of 2002. You can see the rest of the numbers that are here. Again, another interesting one they used to track, it's not on this particular one, was that we were starting 4 new cryptocurrencies every minute of the entirety of 2021. And what that means is no matter which way you think about it, there's an awful lot of data out there and it's growing. So we looked at the total data pieces in here. This is a really wonderful infographic from Martin Hilbert that talks about and shows, as many people have referenced, that most of the data that exists has only been created in the last couple of years, and it's still growing at an incredible rate. In fact, it's growing so far and so fast that our data growth is well exceeding the abilities that we have as data analyst capabilities to actually keep track of it. And so we do need to pay attention to this. There's, again, just a tremendous amount. And what it leads to is something that we will reference in the future here as data debt on this. And the key, of course, with data debt is that without these data structures or data models, your progress, and no matter what you're trying to do, slows, that your quality decreases, that your costs increase, and that your risks increase around that. So let's just sort of do a little bit of level set. Everybody, I hope, is okay with the statement that all organizations have architectures. They're typically some combination of business, process, system security, technical, and of course, data information architectures. The key, if you have an organization, is how well are your architectures understood and documented, because if they are not either documented, excuse me, both documented and understood, they cannot be useful to your organization. And we talk about, from a data perspective, understanding our architecture documented as a digital blueprint. Now, we see an awful lot of people and organizations trying to go digital. Again, it should be obvious from this, but if it's not, you can't go digital without also incorporating data in there. And that data needs to be shared in terms of an understanding between the business and our technical systems and our technical users. If we don't have agreement on those three terms, we end up with the previous slide that I showed you: slower progress, decreasing quality, increasing costs, and greater risks all the way around it. So key for all of this, of course, is to make sure that this communication works out very, very well. I'm working with an organization right now that calls this their ontology. It doesn't matter what you call it. It's the idea of coming up with a common vocabulary and making sure that literally we are all on the same sheet of paper. Because, of course, if we're not, Shannon and I are both musicians, you will note that having musicians sing from the wrong sheet of music really messes up your presentation that you're trying to make. And likewise, it's going to mess up your digitization efforts around that. The amount of work that you have to do to eliminate the things that are problematic about it is what we refer to as data debt. And that'll be the topic of one of the next books that I'm working on with a very favorite collaborator that I'm putting this on. We'll put more about that later as we get through with it. But the idea of data debt is the idea of how much time and effort, how much cleanup you're going to have to do in order to get and be able to actually work with your data. Now let's talk about what we mean by data. And this is one of my favorite slides. If you've seen any of my presentations, you know I rely on it quite a bit. It's a model that precisely defines three very important concepts. And I'm going to start off with the fact 42. And you might say to yourself, oh goodness, what is 42? Well, if you happen to have read The Hitchhiker's Guide to the Galaxy, you know that 42 is the meaning of life, the universe, and everything. Haven't read The Hitchhiker's Galaxy, that's not going to make any sense, although I will put a plug in. It's a wonderful book. 42 also was Jackie Robinson's jersey number and the name of his movie that was out there about that. And thirdly, if we take it as a question of whether Peter is allowed to consume adult beverages in the Commonwealth of Virginia, 42 was my age 23 years ago. So you can do the math and figure out that Peter clearly was able to purchase adult beverages in here. What I've just done here with those three facts is associate them with three different meanings. And data is what happens when a fact is associated with a meaning. So 42 could mean the meaning of life, the universe, and everything, per Douglas Adams, the Jackie Robinson's jersey, or whether Peter is allowed to consume adult beverages. You can see here the rules here are pretty straightforward. A fact combines one or more meanings. Each fact and meaning is referred to as a specific piece of data. We used to call them datum, but we don't try to correct people on that anymore. And the question is, we have a lot of data. Can we tell which of it is useful to us? And that's a really key distinction, because an awful lot of organizations, in fact, do have data, but they don't have an idea of what data is useful to them. Now, the next question then people say is, well, what's the difference between that and information? Information is one or more data that are returned in response to a specific request. So if somebody hasn't asked for the data, it can't become information. But if somebody has asked for the data, then it can become information. Given that rule set, you can't have information without data. You can have data without information, but you can't have information without data. Again, very, very useful, easy to understand, easy to explain to everybody else. And I've always said this, you all, when you get the copy of the slides, you're welcome to reuse these to explain them to folks in your own organization. That's one of our goals here at Dataversity, is to make everybody else smarter about these topics. Then the next question finally comes out to be, what do we mean by intelligence? Over the 40 years that I've been doing this, the terms wisdom and knowledge are often used synonymously in there, but we're taking information and putting it to some sort of strategic use. And having this structure here of useful data, information, and intelligence is actually an arrangement of data. It's a model. The model now you can use to define these three separate terms to people if you ask, or they ask you, what does it mean when you're talking about these things? Each arrangement of data is a data structure. Here's one that shows customer related to a sales order, related to a sales order line, related to a product. This isn't necessarily a right answer or a wrong answer. It simply is one answer to this. And it's any organization of information for making processing of data more efficient. It includes grammar, if you want to get technical about it. It includes object constraints. It includes ordering, whether it's sequential, hierarchical. It includes the uniqueness, the balance of it, the optionality, and also potentially future enhanceability, a need that we will know we're going to need, but we don't have exactly at the moment here. And the question is, how many of these do we want in our organizations? The answer, I hope you agree with me, is as few as possible. The more of these you have, the more complexity that you have, and the more translation work needs to occur between them. Let me give you a very specific example of that. If I gave you an integration problem and said these 6 systems all need to interact perfectly with each other, it's fairly unrealistic, but nevertheless, it represents the upward theoretical complexity of this particular piece. We would have a formula here, n times n minus 1 divided by 2, and say that 15 interfaces are required to arrange perfectly the distinctions between each of these systems. Now, while that's a problem, again, remember our goal here is as few of these as possible. I was permitted to use the numbers from the Royal Bank of Canada that applied to their environment some time ago. They had 200 applications and about 4,900, roughly 5,000 batch interfaces between these. And a question that you might ask is, oh, that seems like a lot. Is the Royal Bank of Canada, or was the Royal Bank of Canada at that point in time, above average or below average? Well, let's just take a quick look. Here are the numbers on the side. If I go from 6 to 60 to 600, you can see that at 600, there are 180,000 possible combinations. So if we put an X on the chart where 200 of them are and show that they had only 5,000, that means that the Royal Bank of Canada was actually below the upward theoretical complexity, about 1/4 of the complexity that they could be with. Imagine the complexity of maintaining 5,000 interfaces between 200 different systems. All of this evolves in a way in which we can now start to understand, and this is a network that I use to describe how all of this occurs. When we look at what's going on in here, we see that there's an as-is component for models. We see that there is a to be, that's the desired state. Notice, however, I've made it a 3-dimensional, and that means we're adding in also models that are validated and models that are not validated. Very important distinction for those of you that are doing real-life modeling around this. If your model is not validated, you're hoping that it's correct, but you're not certain of it. Now, one more set of flavorings, if you will, on this. We can now flavor it whether the models are conceptual, logical, or physical. So this is our framework that we'll talk about for the rest of the session here. To be versus as is, validated versus non-validated, and conceptual, logical, or physical. And if we look at that and say that typically our conceptual model is sort of a narrative, maybe a description of how it is, and that the logical model oftentimes is an actual model of the model, and that the physical is the instantiation of it, all of our modeling changes can be mapped to some transformation in this network. We are moving from a conceptual as is to a conceptual to be, or we might move from a logical model to a conceptual model. That would be a reverse engineering, or we might be doing a logical to a physical model. That would be a forward engineering. Let's look again at these examples. Forward engineering, again, is what we teach students in university how to build. Unfortunately, only 20% of our efforts in IT are spent building new stuff. Enhancing existing stuff occupies 80% of the time, for which our students receive typically 0 experience in those areas. And that is a problem for us. That's one of the reasons you're on this particular call, because we in the academic community have neglected that part of it. So 80% of IT work is some form of reverse engineering. It's evolving the existing systems using a structured technique aimed at recovering rigorous knowledge of the existing system to leverage enhancement efforts. That's going from our physical as is to our physical to our logical as is, and perhaps from our logical as is to our conceptual model. That's what reverse engineering involves. Then we get to a concept called reengineering. You'll see this happens in lots of organizations where they'll use the term. The formality of the term is by first reverse engineering the existing system to understand its strengths and weaknesses. After all, every system has certain strengths and certain weaknesses that we need to understand. And if we really are paying careful attention, we want to bring the strengths forward to our new system and leave the things that are weaknesses behind. In some cases, our reverse engineering extends to the requirements. If you're at the logical model, you are redesigning your system. If you're going back out to the conceptual level, you are in fact changing the requirements for your new system. So if somebody tells you, I can simply take the existing system and move it from place A to place B, this is the worst mistake you can make doing a reengineering exercise. Next, of course, is the key. You have to use this information to inform the design. So here's the yellow arrow showing that you're taking the as-is requirements and moving them to the to-be, or possibly just taking the as-is design assets and moving them to a to-be. Again, incorporating both of those into the design of the new system means you are, in fact, doing a reengineering exercise in the technical sense of the term. If somebody tries to tell you that they are reengineering without first reverse engineering the existing system to understand its strengths and weaknesses, and next using this information to inform the design of the new system, they are simply not doing what they say they're doing. And it is important to point that out because they will not achieve the results that they're attempting to achieve. So hold on for a minute. I'm going to turn this sideways literally. There we go. And now notice what I've done is I put the conceptual, logical, and physical one on top of another. And I'm doing this because the ANSI standard for this also implies the community view of the database here. So that's why I circled the conceptual level on this. They also have a physical representation that they talk about as well. The logical is somewhere in the middle here, sometimes used, sometimes not, but it's important to keep an eye out on it. Notice in the bottom right-hand corner is still our trusted catalog, our ontology, whatever it is that we're working towards in order to keep this. Again, this conceptual level is the highest level of abstraction linked strictly to the requirements. The logical is a refinement on the conceptual model, which talks about the business terminology that's there. And the physical model is necessary because we are going to implement this in some physical model, whether it's in the cloud, which sounds like it's not physical, it really is, in order to do this. And to the degree that databases are well designed, we should be able to make these changes without impacting users involved in this. If this is your first introduction to the Zachman framework, I apologize to you. It shouldn't be, but sometimes it is. John Zachman's been a friend and colleague for decades and deserves every bit of accolades that we heap upon him as the best articulation of what we call a metadata repository framework or metadata characterization. It calls it the enterprise ontology, in fact, and it means it. Now, this is a hard diagram to look at all at once. Don't worry, we're not going to dive all the way through it, but if you Google on anywhere the internet, you will be able to get a copy of this for yourself in addition to having a copy of the slides. Let's look just at these three pieces in respect to the how and what columns. Notice the columns go how, what, how, where, who, when, and why. Those are the 6 interrogatives. And of course, the rows are executive, business management, architecture, engineering, technical, and the actual enterprise itself. Notice I've drawn the lines around the things in the left-hand side there. When we're talking about modeling, this really represents, once again, conceptual, logical, and physical, looking specifically at the what column. In this case, if you're doing this with what and how, then you're integrating a process architecture into what you're doing here as well. Now, hold tight. We're going to change metaphors real quick and talk about bridges. So this is the Millau Viaduct in France. It's the highest bridge in the world at 2007. And it's replacing a road here that I'm outlining in red that required a much longer trip to get around if you didn't have this. Look at it another way. Here's the bridge, and there was the road that took you on the River Tarn. It was business focused. the conceptual model was at an entity level. It provides the focus, the scope, the guidance to the subsequent modeling efforts, and sometimes it's thrown away and sometimes it's maintained, typically not in all cases. In building this bridge, they also followed the same piece, which was John Zachman's wonderful insight with respect to the framework here. Logical models were required to achieve the transition from conceptual in nature to physical in nature. So some of the things that they were looking at here was that the bridge over the River Tarn here was taller than the Eiffel Tower. That is a very significant engineering feat. And it was done with a center pull. It's what's called a dual carriageway, suspended 250 meters above the bridge. And it was very, very light, so they didn't have to build a lot of it. But nevertheless, it was difficult, particularly to sell in terms of the concept. So it was developed to the attribute level. And in our data concept, we're going to understand this at the third normal form. I'll get to that in just a second. Logical models are developed to be refined until they become a solution that sometimes requires additional tailoring and used to guarantee the rigor of the data structures in this case. More often, these are maintained than not maintained around all of these concepts here. So let's look now at the physical models. These are the blueprints for construction. How are we actually going to do it? So here's a picture of one of the towers being built on here. And you can see the trick here was that they were going to build some temporary towers in between the real pylons, those are the red ones, and then take the red ones down and have the bridge, in addition to being what it's going to do, also appearing from a very aesthetically pleasing perspective around this. Here is a model of how this actually worked. We look here, you can see that the bridge is pushing in construction sense towards the center. Now, as it's pushed out here towards the center, one important thing happens at the actual center. When these two halves are joined, the bridge becomes a lot stronger. The fact that the bridge is in fact joined is part of the strength that's involved in this. Very, very key. So again, very different building technique, but obviously very successful in this case. And the next question was, oh my goodness, how do I build this and put the bridge out there in a way that, I'm sorry, I'm going to go back here, in a way that doesn't actually put any sideward pressure on these pylons? Because if I have sideward pressure on them, I will knock them over. So once again, here's the bridge coming together, becoming structurally intact, which is structural integrity. A similar concept exists in data modeling here in order to do this. Here is the little model that shows how this is built. We take the general piece and notice we're pushing it and pushing it and pushing it. It's pushing it slightly upwards, which isn't putting sideward pressure on the pylon. And once we've pushed it upwards far enough, about 2 feet in this case, then we move the second wedge out from underneath it. So through this process, you can see it's moving this piece of the bridge 2 feet at a time in order to put it out there without tipping any of those pylons over. There are similar analogies in our data modeling world here as well. There are things we have to do, particularly with respect to structural integrity and other types of issues. So as a result, we have this wonderful bridge saving us hours of travel on the road. And more importantly, the French government was willing to pay for it, making it a positive return on their investment here. Okay, well, let's now go back into our data world and say, how does this work from an architectural perspective? And the answer is very simple. Details are organized into larger components. This means we have a certain level of intricacy that's involved. The larger components are organized into models. This brings forth the concept of dependencies. And finally, all the models are organized into an architecture, and this brings us to a concept of purposefulness. Purposefulness is really clear. We'll get to that in just a second. The intricacies are held by attributes. These are the things, things. The entities are objects that are organized into models. Those are the dependencies, and the models are organized into the architectures. And of course, it's really hard to envision an architecture, so you end up with some sort of abstract blob, in this case, showing what the actual architecture is in order to do that. Let's also be very clear that data modeling is an iterative process. Data models and architectures are developed in response to needs. The organizational needs change. These become instantiated into a data model that authorizes and articulates information systems requirements. Once again, making sure that we keep our trusted catalog in place that governs all of this. And you can see here we're going through iterations on this. This also is a very good example of why our data should be authorizing IT projects and not the other way around in order to do this. There's a particular reason here, and I use the Hans Christian Andersen's fairy tale, The Princess on the Pea, to describe this. The pea, of course, you can see here at the bottom, is at the bottom of a bunch of mattresses. And if you don't know the story, the princess is sleepless because that pea is causing discomfort. Similarly, data components that are incorrect will cause problems throughout the life cycle of their usage in here. Failure to understand the role of data modeling and data governance locks in imperfections into the life of the application and restricts future investment benefits and decreases the ability of the organization to do leverage around this. Data bad practices account for 20 to 40% of all IT budgets that are devoted to evolving data migration, conversion, and improving the data. And this lack of data governance and lack of data structures, lack of data models takes longer, costs more, delivers less. You heard me say that the first time. So let's take a look at an example of this. This is a product that appears on almost all of the iPhones around the world, Android as well as iOS. It used to be called iTunes, now it's called the music database. And if somebody had developed a music database that ended up looking like this, row one, I've got the purchaser of who bought the song, and here's the song that's in there, and here's the price. Seems like a reasonable thing to put together. But what happens if we delete record number one? What happens to this information collection as a whole? And you can see that if I delete row one, I lose not only the fact that Peter purchased the song called We Met Today, but I also lose the fact that We Met Today costs 99 cents. That is usually unintended and undesired in there. And it's only found out after the system is placed into production. Let's talk about insertion anomalies. Similarly, same database. If I have row 5 and I want to add a new song called Scuba to the database and it costs $1.29, I cannot add that song until somebody purchases Scuba. We can't insert a full row until we have an additional fact about that row. Once again, unintended and certainly undesirable around that. Finally, we get to what are called update anomalies. Suppose I want to change the price of We Met Today from 99 cents to $1.29. Well, if I do that, the current structure requires song. I'm sorry, I went back too fast. Current structure requires song to be examined for every instance, every row in the database in there. And it will catch things like spelling errors. If I called it We Met Toddy instead of We Met Today, once again, these are introducing data quality errors, increasing the amount of data depth that we have in our organizations in order to do this. Unintended and undesirable. There are correct ways to do this. We can optimize for flexibility, adaptability, retrievability, risk reduction. Again, we have to have a goal, a purpose in order to do this. And some of the techniques are data integrity. Some of the things are smart codes bad, dumb codes good, and then architecture table joins. For example, if I take the example we're showing here, or again, the original piece is to store as much as possible, one fact per row. So row 2 is a good example, and that shows both that purchaser number 1 has purchased both the song Sushi Live and that it costs 99 cents. Our way of describing this properly would be to break it out into 2 tables here. And again, I'm oversimplifying the example, but each of these examples causes additional sand in the machinery, and we have to write application code around it if we're going to get rid of all of it. So let's jump into little specifics around the conceptual modeling now. Here again, I'm on the left-hand side of our washing machine graphic that we have here. Motivation is that it gets us a standard vocabulary we talked about before. It focuses analysis on strategic issues and trade-offs, and provides specifications regarding the organizational data objectives, because the data requirements are the most testable, the most objective that we can have in any system description. We don't want to have unvalidated models, because if the models are invalid, we need to put the word draft on them, indicating that uncertainty. We are simply unsure and hoping for the best, particularly if they're used to produce further products. Again, it's hypothesizing rather than actually knowing, and we're documenting the relationship of data things to other things and standardizing on systems-wide definitions and understanding the interactions with high-level process architectural components. Architecture always involves analysis of the model, risk evaluation, volumetric considerations, workforce forecasting, trade-off analysis. Again, you can't be good and cheap and fast. Pick two, and sometimes you'll get a good result. So let's talk about strategy in particular. Strategy is a term that hasn't been used since about, that wasn't used before 1950 or so, when management consultants did it, but that became a thing. It became 100 PowerPoint slides or 100 pages of a book or something in here. Strategy is not useful at that level. The proper definition is derived from the military, and the definition that they use is a pattern in a stream of decisions. Look how effectively Walmart has used that particular definition here. Walmart's definition of strategy is a everyday low price. And that's a wonderful definition for it. Wayne Gretzky has a similarly simple but easy to understand definition of strategy. He skates to where he thinks the puck will be. After all, if you're chasing the puck, you're probably not going to catch up with it. Let me show you a complex example of strategy. The question here was Napoleon at Waterloo, where he in blue is facing the British in red and the Prussian troops in black. And the answer, of course, here was divide and conquer. And this, again, it fits very well, a pattern in a stream of decisions. So let's see this strategy play out in a little bit more detail. First, we hit both armies at exactly the right spot, and then we turn to the right and defeat the Prussians, and then turn to the left and defeat the British. Oh, by the way, all the while somebody is shooting at us. Well, that's a non-trivial piece, and I hope you agree with me that that is a complex strategy. Asking people to deal with complex strategies on the fly is very, very difficult, given all of that. Here's an example of a data model that was for a company that I worked for when I was a manager at one point in time, and I was a staff manager. But notice you could either be an employee or you could be a manager or your salesperson, but you couldn't be both. And at one time they decided that we actually had to sell, which made it problematic here as well. Again, we can come up with cleaner, less complex code, which means it's more maintainable, which means the organization can adapt more quickly to things that are happening. There are lots of other uses of strategic data models. One of the first ones was the Sabre organization, which created flight booking arrangements before they Travelocity and those companies. In fact, Travelocity is still a variant of Sabre, maybe it's Expedia, I forget which one in there. That AT&T, when it was the phone company, had data on everybody in the country who had a telephone and whether they paid their bills, and this enabled them to create a credit card business overnight, which was amazing. Amazon invented something called home retailing by understanding strategic data needs of everybody, and Capital One reinvented the solicitation technique. Each of these is a 1 hour talk. I'd be happy to describe to you on this, but they're very, very good uses of data modeling within there. So how do we do the process? First of all, identify the entities, the business things about which you are creating, reading, updating, or deleting information. It sounds simple, but it's a non-trivial process. Next step then is to identify a primary key, the ability to identify a unique instance in that table among all the other table records that would be there. Then we draw a rough diagram of how those entities relate to each other in there. And then we take the attributes that we've identified and apportion them across the various entities, mapping the data entities to them. Finally, it makes some sense to sit back and take a review, because hopefully our first version is not going to be the proper version. In fact, it's likely to be a little bit of iterations. If your variations are increasing rather than decreasing, you're heading in the wrong direction. The variations should decrease. Once again, of course, keep in mind that you need to have this as a trusted catalog, and that your final variations on this should be refinements of the original rather than completely starting over each case. Here's a specific model for a logical data model that's composed of 5 different views for one of our state agencies in this case. They had a taxpayer view, a governor view, a vendor view, a program delivery view, and a client view. Here's the taxpayer view, where they were concerned with certain entities and how those entities were related to each other. Similarly, here was the client view, where clients looked at the same things, but their payments were different from others. Again, the governance view was more complex, no surprise, particularly given a state government example. Here's the program delivery view, where social service programs and partners were delivering for the local welfare agencies. And in this case, the vendor view, which was supplying as subcontractors within this larger conceptual data model that we had for all of these things. Once again, I've said each time the business glossary is absolutely crucial to have here. It's the start of our enterprise taxonomy or ontology. It defines the initial entities and engages the business community to validate the various entities. Notice here, of course, the concept of versions. Very important to have, because your first version is never going to be correct, and that you should be looking for continual improvement and refinement around this. Let me give you a very specific example of a business glossary here. This was from a wonderful example from a company that I spent a number of years with, Nokia. Nokia started out originally as a tire and rubber products company, then went to consumer electronics. I was there during the mobile phone days. In those days, 2% of the population of Finland spoke only Swedish. So the Finns all became bilingual because they didn't want to risk the possibility of encountering a Swede and not being able to speak with them. Nokia wanted to play internationally and mandated the use of English in all of their meetings worldwide. And lots of words were unknown at the time. And it was bad not to ask questions. This was a wonderful cultural piece that they came up with in here. When a word was questioned, they would look at each other in a meeting. It was wonderful to observe. And if they didn't understand the name of the term, the terminology that was being used, there was a little quick form that they would fill out, building a common vocabulary. That form would go to a group at Nokia headquarters, who once a week would sit down with some alcohol at the end of the week and put together a glossary. So when an unfamiliar term, they'd access the NTB to see if there was a golden definition. If not, they would vote on whether to include it for submission. And then they reviewed the submissions and published this new version of the NTB, the Nokia Term Bank. When I got there, one of the really interesting pieces was we took out our non-Nokia phones, very big faux pas, and I took pictures of this thing because we were trying to figure out what it was. They called it a cruiser collector, and they handed me a 50-page manual on how to use this, not knowing that within a couple of hours I would be in front of their board saying that they had approximately 50 times the amount of documentation on their rubbish than they did how to process their rubbish than they did on how to process their data. Again, real important here. So we've talked a little bit here about conceptual modeling and the idea that within a conceptual model, you should be able to trace things both as is and to be, looking at the what requirements that are there, answering those questions with that particular model. Given any sort of data governance exercise, this is an excellent place to start. Let's now move from conceptual to logical models. We'll drop in here. Again, our middle tier, the orange tier, if we're looking at it that way, logical modeling provides, as I said before, the translation from conceptual to physical, talking about size, shape, provenance, functions. Provenance, by the way, is origin or a reference point from where it came, and talking about downstream uses as well. But it should still be free from technological constraints. In fact, even the selection of a database is a violation of logical data modeling terms. Now, I don't care if you are in Oracle shop and do everything in Oracle or Amazon or whatever. It is inappropriate to talk about it because we're talking about free of technological concerns in this area. Document the primary data decisions and, as much as possible, generating these as opposed to, in fact, creating them by hand. So the logical data models challenge the conceptual model. Just our first approach should be skeptical and say, should we, do we in fact have the logical model correct? Excuse me, the conceptual model correct. It should explicitly incorporate information from existing components now that we're starting to interact with our existing business process. And the logical data models serve as an organizing principle around which system data capabilities are built, facilitating, again, that common vocabulary among business and technical analysts that are there. Here's an example. Standard reporting definition might not provide a context for bed. And if we ask, what is a bed? Well, everybody says, well, duh, it's something that you sleep in. One of the things that Clive Finkelstein taught me is that we should include what's called a purpose statement in here instead of a definition. It's a much better way of doing it. He had a very specific example that we like to use when we were talking about the purpose statement. Why is the information being maintained? What are the sources of information that we have? What are the list of attributes? You can see here we've got bed description, status, sex to be assigned, and bed reservation reason, and a list of associations. Even though I'm not using specific terminology, you can see that a bed has 0 or more associated with a room. Important too, we should include the status of each component of the model, whether it is in draft or hopefully validated before we actually use them. So let's look at this from a relationship perspective. I say, what's the relationship of a bed and a room? Well, okay, beds and rooms are related. That's not terribly useful. We can get a little more specific. Beds are related to rooms. In this case, many beds are related to many rooms. More helpful, but not really. And in fact, the proper definition, at least in this instance, was one room can contain one or more beds in order to do this. This allows us to become more specific and refine this. The starting place for this is typically beds and rooms. That's at the conceptual level. But at the logical model, we're starting to refine this into, each room should have at least one bed, but no more, and possibly many beds. If we say each room should have exactly one bed, that tells us something as well. What if beds can be moved from room to room? Well, that could be a problem in our model. Again, lots and lots of options that are there. Each of these are what are called cardinality options. There can be exactly one or many, eventually one, a little time difference in there, 0, 1, or many, and finally, eventually one or many in order to include these. Again, depending on your level of modeling sophistication, you may just use the first 2 or 3 of these and not the others, but again, depends on exactly what problem you're trying to solve. If we look here at the natural associations between these things, let's take a look. Again, a bed is placed in one and only one room. Okay, so bed can't be in multiple rooms at the same time. Interesting. A room contains 0 or more beds. No problem. Seems very, very reasonable. And a bed is occupied by 0 or more patients, and a patient occupies 1 or more beds. Kind of hard to occupy multiple beds, but if you're being transferred during a time from the intensive care unit to a lesser level of criticalness, in terms of your care, you might actually have 2 beds that you occupy during a single day. Again, once again, remember that trusted catalog has got to be in there as well. So this conceptual model allows us core definitions of these objects. So you can see here we've defined an employee, a support rep, a customer, a company, and a sales rep, and put the definitions between them. I've even mixed the notation here. Here's some graphic notation. Here's a notation that says 0, 1, or more. Again, there's 3 basic ones. The most important thing is to pick one and stick with it. Don't mix them on the same diagram as I've done here. That becomes really confusing. The artifacts at the conceptual level here are really useful. And this is an example that we've used in many, many parts of the world where we simply say, in this case, this was looking at the reference definitions between an account, a charge, a bill, and a subscriber. That may not work for your organization, but I'm sure that your organization would benefit from a similar concretization of this, because the analyst work products become reference material in order to use this. And having everybody have these up on their cubicle walls as they're looking at this or wherever they happen to be working is extremely helpful for getting us all on the same sheet of paper. Again, this is not going to be right for your organization, but it does make sense in a lot of context here to take a look at this. So this is our logical consideration here. Once again, our logical can now be related to the conceptual model if it exists. The logical model can go from as is to be, and of course related back to physical as is and physical to be. Of course, I don't have it on this one, but it's under the thing you'll see in a minute. Remember also, we are talking about validated versus unvalidated components. Very important. Lastly, of course, we get to our physical modeling here. Again, the purple part of our washing machine metaphor here, physical models, again, can be as is or to be, and again, validated or unvalidated. Again, the motivation here is we're developing specifications for production systems. We need a data flow diagram and an entity relationship diagram. I can't tell you the disappointingly large number of organizations that I have reintroduced data flow diagrams to in my career. We stopped teaching them in school when the object paradigm claimed to have solved all of the problems. It clearly didn't and still hasn't, but it has been a help, at least in developing higher quality software better and faster. But the data flow diagrams are still super useful. We've talked, of course, beat to death about the glossary, the catalog, whatever it is. So if the system is in production, a physical data model must exist. And the first question that you would ask is, why would anybody craft data definition language by hand? With the existence of today's tool capabilities, you simply regenerate based on specifications at the logical level and say that I'd like to have that for AWS Redshift or AWS, I forget what the various types of them there, but Oracle, again, different types of productions. By the way, interesting here, one of these physical data models is something that will help your CEO start to understand why you're spending so much on cloud. I don't know if you've all gotten this feedback yet, but the cloud is now turning out to be the biggest component of IT expenditures. It turned out data storage isn't free. So by throwing a lot of data in the cloud, you're actually making Amazon and Google rich and Microsoft rich, but certainly not helping out with any of these things. That's another whole topic. We won't dive into that. You must use this physical data model to create the system that is actually put into production. It becomes the blueprint for physical construction and future maintenance on the system. So the as-is physical models exist, foundational to system documentation, and it's required as a map to access and identify which data in the system you are going after. These, if they do exist and you don't happen to have the models, can be reverse engineered oftentimes automatically or semi-automatically. The 2B models exist as well. This is the specification of the data that can be accessed by the application. Again, specifications that can be generated formally or semi-automatically. Once again, remember draft versus non-draft in that case. So how is the data stored and represented in our systems is the question that most people think is the only question that needs to be answered. I hope with this program today that you've identified the value that exists at the conceptual and logical model, but nevertheless at the physical level, we're talking about persons, places, or things that need to be, once again, created, read, updated, or deleted, sometimes archived, although it's typically not the case. These are attributes that are characteristics of things. So an attribute of me is my first name, Peter, right? And there's lots and lots of others that are there. Let's, instead of talking about Peter, talk about clubs and regions. So here's a entity for region, and it has a club ID in it. And here's another entity called club reporting. So clearly in this case, there's a one-to-many relationship between regions and clubs in the region. Hopefully that makes sense. If we add a couple more attributes out there, region name, region weather, the existence of this attribute tells us that clubs need to be identified separately from one another. The pound sign there knows the hashtag. In this case, it's primary key. If the primary keys match, I can sum these things by primary key and come up with reporting for all of the clubs that are there. It also indicates that club-specific information is likely maintained and that some conceptual level organization exists above the level of clubs. So again, clubs may have status, table assigned, reservation reasons, et cetera, and clearly in this instance, each club must be part of a region in order to be part of this. So let's take a look at these other physical data modeling uses. Again, an organization might describe parts of a thing as ID, description, status, table assigned, reservation reason, taking the ones from the previous page. And it talks about decisions, how to manage each specific piece of information. Each one has direct consequences that occur in this case. For example, a decision to use the above attributes permits the organization to determine if tables are available to be reserved, so I can manage capacity in that case. All clubs have a status. Many reasons can be assigned to the reservation. We might have a free text description in that area, which is not off of a pick list in here. An ID permits each club to be distinct from each other club, and the description is going to allow that, which means that we have model level variances among the additions of keys, and evolving definitions mandate this glossary in order to do this. So all of those models require the same glossary. So the data modeling requirements allow us to understand what the data things are, what do they do, and how do they interact. This represents a means of communicating these precise requirements. Again, the most objective, the most testable requirements that we have in any systems development are the data requirements. And they're maps of these critical business assets that allow us to compose and contain essential metadata for the various data consumers, functioning in the same way as sheet music does for musicians, a single sheet of paper for us. It's essential for other business functions, for example, governance, lineage for analytics, other types of things. And the process is iterative, again, may include these conceptual, logical, and physicals. Modeling is done to accomplish a purpose. There are 5 basic database type structures: a flat file, an index sequential file, a network database, a hierarchical database, and a relational database, with lots of other variations that you hear in the middle. And once again, I can't tell you how many times I've worked with organizations that have built themselves a lake house mess that sits in the middle of everything and nobody can figure out what's in it. Once again, there are ways around that by reverse engineering, but nevertheless, it is still a problem, and it represents a lack of discipline in most organizations. The good example of this, here's a hierarchical database for a standard banner system. And for those of you that are in the academic world, banner is the main ERP that universities are flocking towards these days. And it represents here one parent instance, and all the rest of these are children of that one parent. And by giving you that definition, you now can understand, even though you can't read necessarily very well, how this data model is structured. If we put it out in a flat form, it would be a star schema and would work very, very well there. Just to give you an idea of how much you understand already about data models, a group at one point proposed an alternative to this data model with this data model here. Once again, you can see here that this is a mess, and B certainly doesn't conform to anything or even follow any normal data modeling standards. They could never tell us whether it was as is or to be, whether it was conceptual, logical, or physical, and in fact made a mess, and people actually went to jail because of this. Separate story, you'll have to catch me offline to hear the rest of the details around that. Let's take a look at a conceptual model here from an HR perspective. This is how it might look at the conceptual level. Here's how it might look at the logical level. Very simplified organization, but by the time we take and put that same model in a physical component, it is very, very different. So again, I'm just blowing up that HR detailed physical model to take a look at it. You can see how implementation wise, it comes across very, very differently from each of these other things. So again, we've looked at physical modeling here, and we've spent a little bit of time talking about why modeling in general is important. What are the tenets, if you will, of conceptual modeling, logical modeling, and physical modeling in order to look at these? Let's get to a couple of quick takeaways before we get back to the top of the hour and you guys get to ask some questions around this. Let's dive right in. And first one is, clearly there are correct ways to organize data. Here is the iTunes database that I was showing you a little bit earlier. All of the correct ways to organize data involve data modeling. The modeling can be done because optimization of the data should be done with a purpose in mind, a strategy. It could be flexibility, adaptability, retrievability, again, different ways of doing this. One of the reasons that star schema is so popular these days, because it is very high retrievability in that particular technique. And the techniques may imply data integrity, the use of dumb codes. If you're using smart codes, that is just bad. And that you're architecturally joining your tables in a proper way. You're not just arbitrarily doing them. They have to have common keys, for example, if you're going to design them that way. This is the idea of taking not these P's and turning them into world P's, but something a little bit more useful all the way around. Important distinction here is that data modeling doesn't sound like a whole lot of fun. So don't tell people that you're data modeling. You can get them to sit down and ask them questions about things, and you're just writing some stuff down and kind of organizing a little bit, and then finally making appropriate connections between your objects. As you do that, savvy business people will say, yeah, that's a way of understanding our business that we've never been exposed to before. Keep focus, therefore, on the model's purpose. Again, the reason most modeling sessions go badly is because people lose focus. So a mission in this case might be, we need to understand the formal relationship between a soda and a customer. Now, that's probably not a question that's going to happen outside of Coca-Cola or Dr. Pepper or Pepsi. But I'm pretty sure at Pepsi, they're paying a lot more attention to it now that Dr. Pepper has become the second most popular soft drink, passing Pepsi in this particular instance. So we're going to walk out the door with an as-is physical and logical understanding of this relationship in a model on this. Here's a second example. Again, customer selects and pays for it. Yeah, that's probably an important distinction between just selects the customer. So we have to get people not just to say Pepsi, but to actually buy Pepsi. Here's another one having to do with hospital beds. Again, we're going to walk out the door at the end of this modeling session. We've identified the 3 top characteristics that represent the brand with a logical model. So why is it people are buying this particular brand here? How does our perspective on this change? Instead of just managing information about beds within rooms, that we determine that these hospital beds are going to be the primary means of tracking a patient. Oh, that's it. We'll just put a transponder on it, and we'll be able to find this bed anywhere in the hospital. Yes, hospitals lose patients on a regular basis. So transponders on beds may in fact solve some of the problems that hospitals are facing. Could our systems tomorrow handle the following rule? Is job sharing permitted? An employee can have multiple positions, and a position can be filled by 0, 1, or many employees. The answer to this question is yes. Our systems can tomorrow handle job sharing. And during the pandemic, an awful lot of organizations benefited from this ability to understand their systems through data modeling efforts in this. Our modeling should always be done for business value. Goal is to share understanding that it can be automated to a large degree. And if you're not looking at automation in there, you are wasting your people's time. And more importantly, coming up with a lot more hypotheticals than actual fact-based pieces. That not just defining these things, but making a purpose statement. Modeling is both a problem defining as well as a problem solving activity. And I'll show you an entire dissertation that was written on that in just a minute. The modeling characteristics are going to change for different problems. The use of modeling is much more expensive than picking any specific piece. The models should be maintained as living documents, and they should be available in an easily searchable manner. But utility is paramount, and value is derived from improving the data, improving the way people use the data, and how people's use of the data supports the strategy. It can only be accomplished using an iterative approach, focusing on one aspect of a time and applying the formal transformation methods within that modeling framework. Now, this has been an awful lot of material here in one hour. And as I said before, we've had others that have wanted to contribute to this. It's the wonderfulness of our community here. So first place to take a look is the Data Management Body of Knowledge from DAMA International, the group of which I am the president and have been privileged to be the president for the past number of years on this. We're getting ready to start the work on our version 3, but we've just put out a version 2R of this that will be very, very helpful, a great place to get started on this. I've cited a number of different works in here that you can take a look at. I'm not going to go through all of those, but I do want to take reference to a couple of particular colleagues. My friend David Hay has a wonderful book on data architecture, language, and vocabulary that gets this. I put the Amazon link in here to help him sell some books. And I mentioned the dissertation, our good friend Graham Simpson, who is also a wonderful best-selling author around the world. He puts his hands on anything. It's been great. But this is a book that was actually his doctoral dissertation. data modeling theory and practice, one of the best places that you could start. And literally today, our friend Professor Talheim from Germany sent us a couple of papers in here that he has contributed in here, and he's got some videos that he recommends. I'll put his papers in the inclusion of the slides. So once you get through with the slides, keep going. There's lots more good stuff in there. Finally, Gordon Everest, longtime friend and colleague at the University of Minnesota, probably one of the first and longest serving data modelers here, has a wonderful YouTube video that is really great to take a look at. We are just about at the top of the hour. Steve Hober, my publisher, would be really mad at me if I didn't put my books up. So again, special coupon rate today if you get a chance to go in and grab some of those. And we have some more events coming up, and it's time to welcome Shannon back on. Hi, Shannon.
Hello, that was amazing, Peter. As always, thank you so much. And if you have questions for Peter, feel free to submit them in the Q&A panel of your screen and just answer the most commonly asked questions. I will be sending a follow-up email by end of day Thursday for this webinar with links to the slides, links to the reporting, and everything else that Peter mentioned and anything else requested throughout. So diving in here, got lots of questions coming in. So Peter, is there a template to build an enterprise data model, conceptual and logical, context end-to-end process, including marketing to sales, to quoting, to order fulfillment, to support? Every subject area has many business concepts. Where do we draw the line for conceptual and logical models?
That is a super question. Let's go to a slide that we can talk from here. So again, remember our framework that we use to do this: as is versus to be, validated versus not validated, and logical, conceptual, and physical modeling, right? That's what I want to put up there. So you, as the data professionals, as the business analysts in your organization, are the best determinant as to where those should go. What should be in your conceptual model versus what's in your logical model, what's in your logical model, what's in your physical model. But let's take a very specific example. If you're trying to develop an enterprise data model, I would suggest not trying to develop it all at once before you do anything else. Instead, unless you're installing an ERP, and I'll come back and address that in just a second, it's better to start off with one portion of the business. So let's say you're doing marketing and you're trying to model the marketing portion of the business. Coming up with a conceptual model, moving that model from a conceptual model to a logical model by taking that first draft that you have of a conceptual model and then trying to get to a logical data model of it, should be the case then that reasonably good people versed with the business of marketing can help you to determine what should be in the model and what should not be in the model at the logical level. However, if you're having trouble finding people or you're having trouble getting the conversation started, you can start with the physical as is. Again, if you have a large system that has a marketing module, reverse engineer the marketing module of that. If you have a marketing system, reverse engineer the marketing system, and it will show you what that logical model looks like. What it won't tell you are the definitions. So you can then add definitions that are candidate definitions, meaning your model is unvalidated, and then use that and go into people and say, hey, guess what? I'm going to reward you for finding mistakes in my model. Here's what I think it means. But if they understand that you're trying to learn their business, they're going to help you. They're going to help correct your assumptions and other things, and possibly even correct the way in which the system uses. Oh, yes, I know they say that's the system that they use this for, but we don't actually use it that way. I'll give you a very specific example. My cousin Fred, who I love to refer to, was the #1 craft salesperson for many, many years. And he spent 4 days of his work week out on the road selling and doing a great job. But on the 5th day, he was always at home. And I would ask him, how is it that you get to have every Friday at home? And he said, well, they're making me use a terrible system to report into it. It was an ERP. This ERP was not very well done. So I spend one entire day each week taking my sales data and feeding it into their stupid sales system because it doesn't work the way that supports me as a salesperson. And I said to him, Fred, that means that if your sales system worked better, you'd be on the road selling 5 days a week instead of 4 days a week. And he said, absolutely right. Don't ever tell them that, because I like having my 5th day a week off. But yes, I could be 20% more productive if they would just get a better understanding of their data. Now, I mentioned that's for systems that you're not using an ERP. If you're using an ERP, it's a modular system. It has a sales module. It has a accounting module. It has a production module and other types of modules that you purchase. Those systems are even easier to reverse engineer than the individual systems, because most of there are fewer of them, and they're much better, much more well known to this. And that place can also help you to reverse engineer out of their physical as is ERP system into a logical system in there. And then you and the business people can work out whether something is worth including or not, because that is the primary value. The system will look at it and say, this field is in the database, but I can't tell you whether it's worthwhile to include it or not. And that's where your value as a data person is going to come in. I hope that was a good answer to that, because it was a really great question.
Indeed, it sounded good to me, but we'll see. And then the community, I think, believes so as well. So, Peter,
Absolutely.
for people who deal with just wanting data sets for analytics, example extracts from physical data models, what do we offer them on the power of data models?
Absolutely great answer. So this is the case where we have physical as is systems that are often feeding directly into dashboards and things. And the misunderstandings that occur at that level, because the business users tend not to. I'm going to go to the Zachman framework to explain this particular question. Again, really, really powerful question here, because it illustrates one of the main challenges that we have. And I showed you the whole Zachman framework, but let me dive into just these 3 pieces of it that are here. So when we are looking at the actual physical as is level and connecting those physical as is components to a dashboard, the business value of this becomes lost, because we're dealing with technical specifications. So I've had many, many instances where people say, I just need a dashboard, and the dashboard is built by well-meaning people. And they say, I can't use your dashboard because I don't understand the terminology that's there. Unless you reverse engineer that physical system up to a logical model where you can then talk to the business people about what trends, what a particular data that they're trying to evaluate and examine in there, you'll have much more complexity showing up than is needed. A very specific example was one here in the state of Virginia, where we were dealing with the opioid crisis before COVID hit in there. And it was a wonderful example. There was exactly one person in the Virginia Department of Health that understood data, and they were not reproducible. So it was very, very difficult for them to be everywhere at once. And dashboards were created and put out on a sort of arbitrary schedule, like this will be done next Friday. And so everybody, of course, did it. But we would end up with situations where the same variable would be shown on one dashboard going up, and then on another variable going down. And the sad part was that they didn't have data engineers or data analyst expertise that could help them resolve those issues, because they were mired in the technical details of it. And as I mentioned before, this one colleague who was in the Department of Health with a good data knowledge, and they was simply didn't have the capacity to be able to do this. So very important as you're doing any type of dashboarding or analytics around all of this, this should be done. Now, most cases, your data science community has been given some exposure to data modeling, and they will understand at least the physical as is data, but they're oftentimes trying to derive this logical data on their own. And that is, quite frankly, not the best use of data science resources. Instead, what we should be doing is looking at automated or semi-automated means of moving from your physical as is, the technical perspective, to that logical perspective. And that can then, just in the last example, allow you to engage in a good conversation with the people who are trying to use the products, the analytical products that are developed from this, so they can understand how to do this in a better way. Again, it's a skill we've sort of taught them part of what they need to know, but not enough. And they'll welcome your help in this area because it is a very confusing area to take a look at. Again, great question.
Yeah, lots of great questions today. So Peter, what do you think about semantic data modeling practice, and how does it come together with the conceptual, logical, and physical data modeling? Would you say that conceptual, logical, physical data modeling is more about organizing enterprise data, and semantic data modeling is more about how that data is used in various use cases? Would it be a function of time and cost to decide which of the modeling efforts is skipped or delayed?
I would not, I would let your business priorities drive the business uses of all of this. So semantic data modeling is the idea that we can incorporate some aspects of processing in here, as well as the actual data at rest, which is the typical use of data modeling. And given that, I would, again, it really applies to almost everything. Let your business problem drive the use of this. So if there's an application of semantic data modeling, I would suggest that you need to have the inputs to the semantic data modeling effort be validated physical as is models in order to do this. Because if you try to do it at the conceptual or logical levels, you're going to end up with scrap and rework in your data development process that has to do it. So semantic data modeling is less well represented than the other three types that we've described in here, but at the same time, absolutely useful in here. Let your usage of this drive the particular application of it. If you don't, it's going to be very, very problematic.
Thank you. And Peter, what are some of the software solutions that you recommend to build conceptual and logical data models?
The wonderful thing is that there are actually a series of freeware case tools that are out there. I'm not trying to put anybody out of business. If you're going to do this professionally and get into it, you probably want to make it super, super useful. But you can just Google free case tools. There's several professors who have put together lists for their students that you can take a look at. And it is absolutely possible to do this. I'll take you the other direction though, Shannon. One of the things that we find most frustrating about this is that people like to do this in PowerPoint or in Excel or in Visio or even in something like Lucidchart or Canva. All of these are great packages that do a great job, but they lack the integrated data dictionary, the glossary component that I harped on throughout the presentation. This is what you're really looking for in your use of tools. And if the tool that you have doesn't support an integrated data dictionary, you can very easily build one in Excel. Yes, he actually said that. Build one in Excel to make sure that you do it, but it requires then much more discipline to be able to use in order to use it correctly.
I do love a good Visio flowchart, I have to admit.
Mm-hmm. And yet Microsoft for years and years has had that as a request, and they will not put a data dictionary in it. It's just super frustrating. Microsoft really doesn't understand data structures as a company. I think we can say that authoritatively after all these years.
Well, that might be objective, but so Peter, if information is data that is returned when someone asks for data, then does it mean that when we conduct interviews, what we capture is information?
Absolutely. Good point. So being back to this chart, which is what the questioner is referencing here, if you take a look and say, we're trying really to figure out what are the precise pieces that people are doing, this is the essence of it. What facts and what meaning are we putting together as data structures that people are requesting from us in order to gain access to information? And of course, there's a third layer on top of that, which is which of those are considered to be of strategic use. But you can take this information and reverse engineer it out into the facts and meanings, which allows you to develop the data model that supports the use of useful data to supply information needs to a particular business function.
Thank you. And the first step in creating a conceptual data model is to identify entities. What is the best way to identify your entities? I have people even asking, what is an entity, since the word has so many meanings in IT?
It really does, and it's unfortunate that it has so many meanings to it. Let me find a spot for this. The way of building models is actually pretty straightforward, and I've worked for companies that will oftentimes want you to have a model developed as a result from this. If they won't tell you, or they don't have a good idea what these principal entities are, you can find out about it by reading the company's corporate K1 or annual report. They will use nouns in that report. I'm not saying go through and find all of the nouns, but if they are worth mentioning in the strategic report, they are probably components of your conceptual model. So just put on a piece of paper, again, or a Visio chart, if you don't have access to the case tools, or find one of those free case tools that are out there. Again, just Google it. Like I said, there's good lists that people have maintained, and start to define those entities. Okay, these are business things about which we are creating, reading, updating, or deleting information. And each of these as conceptual models, then we want to flesh out in more detail. Sometimes people say, don't bother putting anything other than the entities and their relationships between them. Again, just getting to this level of specificity and leaving out the attributes from it. That's perfectly fine for most conceptual models. Remember, you're not doing a model for the sake of doing a model. You're doing the model so that you can have a conversation with business people about what are the things that are important to them, and how are those things eventually represented in systems. Let me give a specific example on this one, Shannon. One of the corporations I worked with was having an argument among the various managers as to whether a project could be owned by more than one department. And I found this was a very interesting way of describing this. Okay, well, they had a policy. Each project should belong to one and only one department. There could never be any shared pieces between them. And I said, that's fine. We can certainly go to it that way. But I had gone to the database person, the DBA, who actually built the database that maintained information about projects and ownership. And that individual had made it possible for multiple departments to own a project. So even though it was, quote, against policy, it was actually physically quite true. And many departments had figured it out and were circumventing those rules and saying, no, we do shared projects all the time. The systems support it. Now, think about the opposite. If you wanted to have that be true, and yet the system didn't support it, you would have a lot of work that would have to be done to maintain information on each of these projects. It would be a very difficult, complex task that would have to require code where something should more appropriately be stored and maintained in a database in order to do it. Again, great question.
Very good question. So, Peter, what tools do most groups use to document conceptual data models? Ontologies, data catalogs, or approaches changing?
More and more, especially with the advent of data governance. Again, most of you who are young don't remember a time before we talked about data governance as much as we do, or had conferences on it, but we've always done some aspects of this. We used to call it data administration, but that wasn't nearly as sexy as data governance is. And don't get me wrong, we're not going to say data governance is sexy either here, Shannon. That's we'll leave that to the people at the conferences to help identify those particular attributes there. Yeah, it's absolutely the case that a glossary can tell you in a narrative sense what that conceptual model should look like, but it's so much easier to show them a picture of it. And so in almost all cases, even though you maintain things in multiple places, the key is to have them integrated. Because if I make a change to the diagram, I would want the definitional part to be updated. And if I made a change to the updated part, I would want to have the diagram updated as well. And it's so easy to do that. Case tools are not expensive, but they're for some reason not even taught. So most people, literally the last 30 years, we have not taught people that these case tools exist. And so they come out and they discover this and they go, oh my gosh, why didn't they tell me about this in college and university? And I don't have a good answer for them there. I try to introduce the concept to all of my students, but I'm only one professor. And there's an awful lot more that are teaching it without the benefit of all of these things. So Yeah, you can do it from a spreadsheet, but it's not the best way to do it. It's usually a combination of some sort of glossary being supported with a case tool and again with a generative capability so that you go from one place to the next. The proper case tools will generate automatically your glossary and generate automatically your data model. And you never need to draw or redraw anything. By the way, one more piece. Let me go just very quickly to another slide on this. Sorry, it's going to take me a second to find it, but if we go to the business of moving back and forth between these various components, if you have a logical data model and you're then hand generating your physical as is data model in there, you run the risk of introducing errors into it, which means you're going to have to maintain it. The proper way of doing this should be to take a validated logical model and run it through a case tool that will automatically generate the data definition language in whatever form you need, and it will put it out there in Azure format, or it'll put it in Google format or AWS format, or even back to good old standard on-prem Oracle DBA format in order to do this. That's a much more efficient way to do this, because then you're not maintaining anything, you're simply regenerating it from specifications each time. And if the specs are wrong, you regenerate, you don't time correct it. Again, I don't know why we don't teach this, but not in charge, so. Right, I guess if they did, they wouldn't need us, right, Shannon?
This is very true.
Mhm.
And I love this next question. We get this question a lot, but I love the new format. How to convince executives about the importance of data modeling in this Gen AI era?
Great question. The real key to them is to show them the possible things that can go wrong if you don't. And you don't even need to make a model to see it. Again, take as an example, just some sort of business context that you're trying to get across to them that could be possibly misinterpreted. Again, a noun that has multiple meanings, synonyms that could go unnoticed or uncaptured on this. And show them that this, again, take the example of my cousin Fred. Believe me, the people at Kraft are kicking themselves because they could have gotten 20% more productivity from him every single year that he worked there. And he worked there long enough to collect a really hefty pension from them in order to do that. Show them a specific business example and say, the way you resolve this problem is by formally specifying our use of these definitions. So we're not just saying, again, I'm trying to think of an example here. I used to have a whole list of them. I guess I took that out of this particular presentation. Well, I'll give you a very specific example. This one comes from the military. If I use the term secure the building, it means different things to different parts of the armed forces. If I say secure the building to the Marine Corps, they send in a company and they clear the building, everybody, and they form a defensive perimeter around it. If I say secure the building to the Navy, they turn out the lights and they lock up and leave, because that means leave the ship and everybody, just so that it's sitting there secured. If I tell it to the Air Force, they put out a 3-year lease with an option to purchase the building. Again, absolutely the same terminology, but different interpretations by each part of the armed forces in order to do that. There are examples of this in each of your organizations, whether you're talking about organ transplants or puppy dog rescues or anything else. There are all kinds of business terms that overlap in all languages. And people used to say, well, that's just English because English is such a screwed up language. And yes, it is, but they exist in all sorts of other types of languages too. And again, if we had more time, I could give you more examples, but I guarantee you guys are the most expert at this. Find those examples, show them to the executives and say, how do we avoid making this mistake? Well, by formally specifying it. And what's the formal what form does the formal specification take? It's got to be in the form of a data model.
Yeah, Peter, we are very excited here at Dataversity. Gartner has projected that training budgets for data management are going to increase dramatically by 2027 because the vast majority of AI projects will fail because they skipped things like data models and standard data management practices.
And have I shared with you my license plate?
No.
GIGO. Now, Shannon's laughing because she knows it stands for garbage in, garbage out. And of course, that's exactly the problem with most AI. If you have a bad quality data going into it, let's just say that you take ChatGPT as your input, for example. We know that ChatGPT is a B student, gets a grade of 85. It means 50% of the data that comes out of ChatGPT is absolutely incorrect. Well, if we're using that to feed into our AI system, and then we're using that AI system to do other things, that means we're compounding that rate of 15% on a periodic basis, which does not lead to happy outcomes. Yes, absolutely. Again, AI is a big, big challenge. It's not that AI is bad, but if you feed AI with bad data, you're going to have a problem. And misunderstanding how your data is structured into there is the very least that your data scientists need to understand when they're trying to do their various wonderful things that they can do with various types of artificial intelligence these days.
Indeed. We've got about 5 minutes left here, Peter, so I'm going to try and slip in as many questions as I can here with the remaining time. So how do you promote the use of the conceptual model?
It's the hardest of the three to justify. The real key to it is to take your logical models, maintain those at your corporate level, and then remove a lot of detail to show your conceptual. That way you don't have to maintain a separate set of models. Once again, if you're in a case tool environment, you can push a button and it will do all of those things for you. If you're not in a case tool environment, what you're talking about is simplification so that you come up with concepts that are up there as opposed to specific business terms on that. But that is a really, really good way. I spent several years at one organization that was determined to try and come up with a very good set of models, conceptual, logical, and physical for their major systems. And we finally did enough calculations that determined that the best we could do would be that we'd create very accurate models of the way their systems used to be 3 years ago. And that is not a happy prospect. It's certainly not a positive return on investment. But if you have a logical model that is maintained and you generate your conceptual models from there, it's a much easier proposition to sell.
Perfect. I'm going to flip in at least one more question here. So what are your thoughts on how to keep a discipline on developing and documenting data modeling in a business scenario that demands speed at its maximum expression? Is this something that needs to run independent of projects and design ahead of needs and requests?
The cadence, again, great question. The cadence of data is different from the cadence of software development. And that's important to recognize. Software development needs to be separated and sequenced after data models. Data is a shared resource, and we want to make absolutely certain that our shared resources are developed at a different rate, a different speed than our applications development. If you are doing development sprints and your data requirements are uncertain, you are throwing money down the drain. So make absolutely certain that you separate and sequence your data development from your software development, and that your data development should drive, in fact, your software development. Only those requirements that are fully understood should you spend money on software development activities in order to do. And the key for that is to understand that data doesn't change on a regular basis. Data tends to remain the same. One of the fortunate things about being on the planet as long as I have been is that I can go back to companies that I visited 40 years ago and show them that they are making exactly the same products and services from a data perspective as they were 40 years ago. Most organizational data requirements evolve much slower over time than do their IT needs. And that's the reason for the disconnects that are there. It's a really good question. It's a tough one. But if you look at what's actually happening out there, you'll see that the data requirements evolve at a much slower rate. Therefore, you can do these things to be in front of that development. And in fact, by doing that, you can actually determine which software activities are going to be more valuable. Again, I'm defying people at this point in time to show me anybody that's gaining any sort of business advantage from moving from Windows 10 to Windows 11, even though that's something that's high on many people's technology roadmaps these days.
Perfect. And Peter, well, we've got just less than a minute here. So I'm afraid that is all the time that we have for questions. Such good questions coming in. Thank you everybody for being so engaged in everything we do. Really appreciate it as always. Peter, thank you so much for another fantastic presentation. And just to remind everyone, I will send a follow-up email by end of day Thursday with links to the slides, links to the recording and everything else. Peter, thanks so much.
Thank you, Shannon. Pleasure as always. Everybody have a great day. We'll talk to you next month.
Thanks, y'all.